All right, guys. So let's go ahead and dive into chapter 3 here. We'll be doing acids and bases. This is going to be our first discussion of chemical reactions in organic chemistry. And so we're specifically going to focus on acids and bases first because there's something that you guys have already been introduced to at least a little bit, right? Hopefully we all remember our titrations from general chemistry, of course. So then you'll see these reactions that you have somewhat familiarity with, but in this context of organic chemistry. So we're going to deal with them in the same way that we'll deal with a lot of the reactions that we'll see later in the semester as well. So it should give you a flavor of what the semester should look like. First, we're going to talk about the anatomy of an acid-base reaction, okay? So obviously, an acid-base reaction is between an acid and a base. But first, we got to go ahead and define what that means. So we're going to start out this chapter with what's called the Bronsted-Lowry definition of an acid and base. This is sort of the most common one. And that is where an acid donates a proton and a base accepts a proton. All right, so an acid is the person or the molecule that's getting rid of that proton, and a base is accepting that proton. And by proton, let's make sure what I mean here is a hydrogen cation, right? Hydrogen, when it's neutral all by itself, it consists of one proton and one electron. When it gets rid of that proton, when it gets rid of that electron, all that's left is a proton. So when we say it donates a proton, accepts a proton, we're talking about this H plus here, or the hydrogen cation. We more commonly refer to it as a proton. Okay, so let's take a sort of very common acid-base reaction here where our acid or proton donor is hydrochloric acid, HCl, and our base is this famous hydroxide base that we use quite often in the lab. Here, the base will be our proton acceptor, as always. And so if we are going to follow what exactly happens in this reaction, we can color our hydrogen red here so it's easy to tell what's going on. The acid is donating that proton, so it gets rid of it, and the base is the one that accepts the proton, okay? So this bond right here in my acid gets broken, and a new bond is formed between the base and that proton, okay, right? The base is accepting the proton. Okay, so that covers the left-hand side or the reactant side of my chemical equation. Got to designate the acid, which is going to be donating the proton, and the base, which is going to be accepting the proton. So now let's focus on the product side over here. These are what we call the conjugate acid and conjugate base. So let's figure out how we label these. Okay, so the conjugate acid is the result of the base accepting a proton. So it's the species that's formed when the base accepts the proton. So let's just look here. In this particular reaction, my base is water. And so the conjugate acid is the result of that base accepting a proton. Okay. Now here, notice that in this particular example, water is the base. Okay, we don't really think of water as a base very often. That's one of the things that I want you to keep in mind when we're studying acid-base reactions, is that we're not talking about a compound that's always an acid or a compound that's always the base. Different compounds can play different roles. The same compound can play different roles in different reactions. So water in this reaction is playing the role of the base. It's accepting the proton. We may see examples where water is playing the role of an acid. It's actually donating a proton, okay? So you don't want to think of acids and bases as being these like ironclad categories in your mind. You want to think about them as being roles that molecules are playing in a reaction. Who is playing the role of the acid donating the proton? Who's playing the role of the base accepting the proton, okay? So then on the other hand, we have the other species, which is our conjugate base, and the base is the result of the acid giving up a proton, right? So that is the species that's formed when my acid gives up the proton. So in this case, my acid was HCl. The conjugate base is going to be what happens when HCl gives up that proton, or i.e. just the chloride ion. Okay, so now let's look at another example down here. And here we're going to go in and fill in with our own labels of what a conjugate, the acid, the base, the conjugate acid, conjugate base. Okay, so first step, we got to figure out what proton is being exchanged, because that's the nature of an acid-base reaction. They actually sort of made your life a little bit easier by color coding it here. So we have this red H that's being exchanged in this reaction, right? I guess one of the things that I should have said, the basis of all chemical reactions are bonds are being broken and formed, right? So when we're looking at a chemical reaction and we're trying to identify what's happening, we want to figure out which bonds are being broken and which bonds are being formed. Okay, so I see this red hydrogen is switching places. That means that this bond right here is being broken, and this bond right here is being formed in my chemical reaction. Okay, so that means that this species water is in this example is the proton donor. So here, this is my acid. So now we have two examples, one on top of each other, where water is playing a different role. So again, that's how I want you to think about these acid-base reactions, is what role is the molecule playing? And that, of course, means that this, what's called a butoxide ion, is my base. I think I've said this before, and I just want to stress it again. I'm going to be using the names of these molecules. We actually haven't even gotten to nomenclature yet. It will be a big part of this semester. Nonetheless, I think it's going to be helpful to just hear it, to be immersed in it, so that when we do get to the point where we are learning this, they don't sound like completely foreign words. You're kind of like, oh yeah, I remember him saying that before. Okay, so now we got to figure out what the conjugate acid and conjugate base is. Well, remember, the conjugate base is the result of my acid giving up a proton. So if here's my acid, then the conjugate base is going to be once that molecule has gotten rid of that proton. So that would be this guy. And likewise, my conjugate acid is the result of my base accepting that proton. So this is my okay. So that's step one skills that we need for acid-base reactions, is to be able to label our reaction, balanced chemical equation with who the acid is, who the base is, who the conjugate acid, and the conjugate base. All right, so in addition to being able to label our balanced chemical equation with the acid, the base, the conjugate acid, the conjugate base, we're going to need to be able to come up with the structure of, for example, a conjugate base given an acid. Okay, so let's do a few practices here. Okay, so actually, let's go ahead and do this. So this is the hydronium ion H3O+, okay? And so if this was my acid, how would I be able to tell the structure of my conjugate base? All right, so first of all, what does an acid do? An acid donates a proton. So I know that I'm going to have one less proton in my conjugate base than I have in my acid. Question is which proton is it, right? So in this example, it's fairly straightforward because, you know, they're all the same. But I wanted to give you a few tips on recognizing which protons would actually be lost. So first of all, an atom has to have a hydrogen bound to it in order to be able to donate that hydrogen, right? If you're trying to identify which atom actually loses its hydrogen, if it has a positive charge, that's a guaranteed starting point. So in this example here, my oxygen has a positive charge. That means that one of these hydrogens is going to be the one being donated. Again, kind of a simple example because they're all the same, but nonetheless, so that means I'm going to get rid of that hydrogen to make my conjugate base. Now, the only other thing that we got to watch out for is charge, right? When you're donating a proton, that means that you are losing a positive charge. So the net charge on your molecule has to decrease by exactly 1. In this case here, this pair of electrons ends up coming back to my oxygen here, and so I get rid of that positive charge. There are 2 pairs of electrons. I should have drawn in my 1 pair over here. just to be good. Okay, but so given an acid, we're able to find the conjugate base this way. So the conjugate base for the hydronium ion is just water. Let's do another example here. Okay, so this is what's called acetic acid. And unlike my other molecule here, there's actually two different options of hydrogens that could be donated that I got to choose from. Because I have this one on this OH group, but also I have these three implicitly drawn hydrogens back here. So the question is, which one of these atoms is going to lose its hydrogen, the oxygen or the carbon? Okay, well, none of them have a positive charge, right? So I can't use this rule here. The next rule is that it's going to be the most electronegative atom that has that hydrogen. Okay, so in this case, it's going to be the hydrogen that's being donated is going to be bound to that oxygen. It's going to be the more electronegative element. Okay, so that means I got to get rid of that hydrogen on my acid there. And then again, I got to think about charges because I'm losing a positive charge. That means that that atom will have a negative charge associated with it. So my formal charge on that oxygen atom becomes -1. If I wanted to draw in my lone pairs, that means I would have 3 lone pairs, right? Remember those simple rules for oxygen when it has a formal charge of -1, has 3 lone pairs, 1 bond. Okay. And now, and actually this maybe was a little bit of a simple example as well, because you would have recognized this as a carboxylic acid group. So a group that regularly plays the role of an acid. But now let's do one molecule where we don't regularly think about it as an acid. So this would be ethanol, which is an alcohol. Just like water, you can see alcohol is playing the role of both acids and bases. If it's going to be playing the role of an acid, then it's going to be donating a proton. So if I'm going to figure out what its conjugate base is, I'm again going to look, is there any positive charges? No. So that means that the hydrogen that's going to be removed is going to be removed from the most electronegative atom. So in this case, again, it's that oxygen losing that hydrogen, and then I have to remember to subtract 1 from the formal charge of that atom. So again, I'm left with an oxygen with a formal charge of -1, so 3 lone pairs. Okay, and then we want to be able to play the same game starting with a base and being able to figure out what its conjugate acid looks like. Okay. So let's, again, let's start with a fairly common one. And that is the hydroxide ion. So now, if this is my base and I have to draw its conjugate acid, of course, remember a base does what? It accepts a proton. So that means I'm going to have to add another proton to that molecule. And not only that, I'm not just adding, or it's, how do I say this? Remember that I am just adding the proton, not any electrons along with it, which means that the net charge on that molecule needs to go up by +1. So in the case of hydroxide, it had this formal charge of -1. Well, in my resulting conjugate acid will be neutral. There will be a formal charge of 0 on that oxygen. In terms of identifying where that hydrogen is going to go, that's sort of the hard part of the base. Whoops. In this case, it was pretty straightforward because I didn't, I wasn't going to put it here, obviously, right? Nonetheless, similar to the previous example, or analogous at least, if you have a negatively charged atom, that would be the most likely one to accept that proton, right? Because then it gets to be neutral. The other situation might be to look for the least electronegative. So in this case, least electronegative atom that has a lone pair. So let's do, again, ethanol. We saw this behaving as an acid before. What does it look like when it's behaving as a base? Well, even though oxygen's the most electronegative atom in this structure, it's the only one that has a lone pair. You have to have a lone pair to be able to behave as a base, to accept that proton. So if I'm going to draw the conjugate acid, I'm going to, again, let me just duplicate this here. All right. I'm going to add another proton, right? The base is, again, it's accepting a proton. So I'm going to add another proton onto that atom with the lone pair. Okay. And then again, I got to remember that that's going to increase that oxygen charge by +1. It was neutral on the left as a base, which means that it's going to be +1 over here on my conjugate acid side. Okay. So let's just do one more example here. Oops, not 3, 2. All right, so now I got two functional groups in this molecule, an amine functional group and a alcohol functional group. So which one is going to actually be the base, playing the role of the base? It's got to be accepting a proton. Well, again, it's going to go on the less electronegative atom that has a lone pair. In this case, nitrogen is less electronegative than oxygen. So the conjugate acid, again, I'm just going to duplicate this. The conjugate acid is going to be the protonated form of the base. So I'm going to stick a proton on my base. And then again, I got to pay attention to formal charges. My formal charge has to increase by +1. So that means that I will have a positive formal charge on that nitrogen. All right, so not only do you need to be able to label your balanced chemical equation with who's the acid, who's the base, who's the conjugate acid, who's the conjugate base, but also given an acid-base pair, can you tell me what the conjugate acid is and what the conjugate base is? Being able to derive those structures from your original acid and base is a really important skill.